we were talking last lecture, we did the little demo, and we started introducing the concept that we're going to need to deal with rotating bodies if we're wanting to deal with dynamics. So how we make objects rotate when we apply forces to them, how rapidly they will rotate, so effectively coming up with the rotational equivalent of Newton's second law. And we demonstrated that clearly for forces, we can't just use forces, we introduced this concept of moment, and then right at the end I did a demo that not only the mass is important, but where the mass is located, and we'll get onto that in a slide or two. So first of all, just to refresh ourselves here, this is just a quick example on how we calculate the net moment on an object. And so what we've got here is we've got a bar that's pivoting about some axis here, and we have two forces acting on it. So we've got one force acting up here at the end, another force acting down. So for example, this might be a shelf where you pivot it against the wall here, and you have you have some rope at the end holding it up, and you have some object on the shelf with a weight of 10 newtons. So if we look at this, what we do when we add moments is moments are vector quantities, so we have to worry about the direction of them. And if we look at this thing here where we have our bar, and it's rotating about this point here, then what we do is we look at the moments. So in this case, they're all simple and orthogonal, so it's easy to calculate them. We don't have to worry about taking the perpendicular components because all the forces are perpendicular to their lever arms. And so if we do this, we calculate the moment of this. So we're told that this is 4 meters here, and this is 2 meters. So the net moment to calculate the net moment, we have to decide which way we want to take as positive. So we can choose, right? There's no predefined way. If we're just doing a simple two-dimensional problem like this, we can choose whether we want clockwise or anti-clockwise to be positive. Well, since this looks like it's probably going to have the largest moment, I am going to pick this way as positive, right? So I'm picking anti-clockwise or counterclockwise as the positive direction, right? That's a completely arbitrary choice. You get to pick whichever way you want in your question, unless the question, of course, tells you beforehand. So if it tells you there is a moment of 20 Newton meters applied in a clockwise direction, then that's telling you that clockwise is positive in the question. So you do have to look for clues in the question as to if the question tells you a positive direction, but if it doesn't, you're free to pick. And in a lot of questions, you'll have some sort of equilibrium problem like this, and so you can pick whichever direction you want to be positive. So we're going to pick counterclockwise as positive. So if we do this, we've got to add up all the forces, so if we all the moments. So if we look at this, we have a 20 Newton force acting at a distance of 4 meters away from the pivot. It's wanting to make it rotate in an anti-clockwise direction, and that's the same way that we've chosen to be positive. So this force here is going to generate a positive moment, and the size of the moment is going to be the perpendicular component of the force. Well, that's 20. It's the entire force multiplied by the distance, which is 4 meters, right? Now we want to look at this moment here, and at this point you can see that you've got 10 newtons, but it's acting downwards. So this is going to try and rotate it in the opposite sense. It's going to try and rotate it in the clockwise direction. So this is opposite to our positive one, so it's going to be a negative moment, right? So put in the minus sign because it's going the opposite direction. The magnitude of the perpendicular component is 10 newtons, and the distance from the pivot point is 2 meters, right? So that's Zach's contribution. And then finally here we have a 10 Newton force acting at the pivot. Now this is an important point of what a definition of a pivot is, right? So if you have a pivot point, say like a hinge on a door or something like that, a hinge can exert a force. The difference between a hinge and having something fixed, as in sort of nailed to the wall, right? The difference between those two is that if you nail something to the wall and fix it, then it can exert a moment, right? So if I take a plank of wood and I nail it to the door and nail it to the door frame and I try and move it, that is going to resist my rotating motion, right? Because it's not only exerting a force, it's also exerting a moment. If I put a hinge there, then it can still exert a force, but what it cannot do is exert a moment, right? So that's actually an important definition, that a fixed equals moment plus force, pivot, no moment, but still a force, right? And that's something that people sometimes forget, is that if you have a pivot, you still can get a force exerted there. And this is an example of it here. We've got a hinge here, a pivot point, and we have a force being exerted by it. But if we're wanting to calculate the net moment, then this is 10 newtons multiplied by 0. So it's a pivot because although there's a force acting there, it's still not exerting a moment on the object. It's just exerting a force, and that has 0 moment about the pivot point because it acts at the pivot point. So this adds 0, and so if we add all of this up, we've got 80 minus 20, and so we end up with a net 60 Newton meter moment in the counterclockwise direction, right? So any questions on that? Because you're going to be doing, this is sort of a very simple example, but we're particularly when we get into equilibrium problems, we'll be doing this a lot with forces at angles and things. So you need to understand the basic sort of physics of what's going on there. Okay, so let's do another example. So now what we're going to do is we're going to consider a boy playing with a toy plane. Okay, so let's consider here, we've got a boy here with a toy aeroplane that's going round in a circle, and it's attached to a piece of string, and obviously there's the plane engine here generates a force, and of course it generates a force to cause the plane to accelerate in a tangential direction, right? So we've got a tangential force here causing the plane to have a tangential acceleration. So if we look at what's going on, what we've got is here's our pivot point. I'm not going to try drawing a plane. We'll just put it in as a ball, right? And we have a transverse force acting on that object. So if we look at Newton's second law in this direction, there's also, of course, a tension on the string, which is what's making it go round in a circle. But what we're going to do is we're going to do Newton's second law in this direction as positive, and then, of course, what we get is we get that the force is equal to the mass times the acceleration in that direction. And since we're doing it tangentially, we've got the tangential force is the mass times the tangential acceleration. So we know, though, we can relate the tangential acceleration to our angular acceleration. If you remember, we had here that the tangential acceleration was equal to r theta double dot, right? So if we look at this, then we can rewrite this as the tangential force is equal to the mass times the radius times theta double dot, right? Now, this, of course, is not particularly useful because we don't usually know what the tangential force is. What we know, or when we're doing rotational kinematics, is rotational problems, is we want to have a rotating quantity. So instead of a linear force here, what we actually want is we want the moment of that force, right? So we don't want to be writing down the tangential force. We want to write down the moment that's applied to the system. Because obviously here we can think of it as a tangential force, but in general we have moments. So if we rewrite this as r times the tangential force, right, that converts it to a moment, because that's the moment of this force about the pivot point, and then we get mr squared times theta double dot. So this here is the moment of the transverse force. So what we end up with now is we end up with n, the moment, is equal to mr squared times theta double dot, all right? So this is our angular acceleration. So if we look at this, we've got the equivalent to force, right? This is our equivalent to force in the rotating world. We said that moment of a force was going to give us how much rotational oomph, as it were, the force had, and that was what we used when we're doing rotational problems. If we look at this, this is our equivalent to linear acceleration. That was what we replaced linear acceleration with, was angular acceleration when we're doing rotational problems. And so what we're left with here is this is equivalent to mass, right? Because if we look at it here, we've got force is mass times acceleration, right? That's Newton's second law for linear problems. What we've done is we've converted this into moment of a force. We've converted this into angular acceleration. And what we've got left here, this funny mr squared quantity, is the rotational equivalent of mass. And what we call it is, it's not called mass, it's called, just like we have moment of a force, this is called the moment of inertia. Right? So it's the moment of inertia, and that tells us how much an object is going to resist being turned. And just like the demo we had right at the end of the last lecture, right, you could see that the position of the mass is going to be important, and you can see that from here because there's an r squared term in it. So what that means is the larger r is, the larger r becomes, the larger the moment of inertia becomes, and that means the more the object will resist being rotated about that axis, right? Because this, remember here, if you think of it in terms of the plane, this is our distance of the mass m from the axis of rotation, right? So the further the mass is from the axis of rotation, the harder it is to make the object rotate. And with the demo we did at the end of last lecture, you could see that when I moved the masses out to the ends of the arms, the thing accelerated a lot more slowly. And this makes sense because if you think about it, right, what's going on here is if I've got a mass on the end of a string here, and I have a particular angular velocity, I've got a linear acceleration at here that's equal to r times theta double dot. That's its linear acceleration. So if I have something that's got twice the radius here, then my acceleration here is equal to 2 times r theta double dot. If this is r and this is 2r, and these are both mass m, right? Then clearly here, for the same angular acceleration, this one that's twice as far from the axis has got an linear acceleration that's twice the magnitude of the first one. And so, of course, that means that the inertia of this mass is going to, it's for the same angular acceleration, this mass has twice the inertia of that mass has twice the effect, right? Because to get the same angular acceleration, the linear speed of this mass would have to be twice the linear speed of that mass, right? The further you go from the axis of rotation, the faster the mass is going to be traveling. And so for the same angular acceleration, you have a larger linear acceleration of the mass. And so therefore, that mass is going to resist an angular acceleration twice as much as a mass that's half the distance away from the axis of rotation, right? So when it comes to rotating systems, it's not just enough to know the mass. You have to know where the mass is located, right? And we'll see how to calculate this for objects in a minute. And so the result is that we end up with we write this as an I, the moment of inertia, and so we end up with this rotational form of Newton's second law, that the moment is equal to I times theta double dot, right? So this is force is equal to mass times acceleration, but now for an object that's going around and rotating, right? But the same principle applies, right? So this leaves us with what is this new concept we've introduced, this thing called moment of inertia, right? We want to know what this is, and more importantly, we want to know how to calculate it for physical objects. So if we have a system of physical objects, right, we talked about the the single point mass of the plane, the toy plane, and that was just mass times r squared. So if you've got a single point mass, it's very, very simple. It's just the mass times the distance from the axis of rotation squared. If we have a series of point masses, right, then we can just add the moments of inertia together, as long as we're adding the moments of inertia about the same axis, right? That is an important concept. You cannot just, so like masses, it's a scalar quantity. You can add it just like you can add mass, but with the calculation of moment of inertia, you no longer just have the mass, you have the mass in relationship to an axis of rotation. So if you've got a common axis of rotation, you can add the moments of inertia about that common axis of rotation. But I can't, take the moment of inertia of this object about an axis of rotation on the table and the moment of inertia of this object about an axis of rotation on my shoulder, right? Because if they've got different axes of rotations, you can't add the moments of inertia. So be careful when you're doing problems that you are always adding the moments of inertia about common axes. That's a very easy mistake to make, is not to have them about the same axis. Okay, so that's great if we've got a series of point masses, but this is the part that I know you're going to love. What happens if we have a solid object? And this is the one bit of the course where calculus is mandatory, right? Well, one of the few parts of the course where it's mandatory, and it also gives you an insight into how we apply calculus typically in a lot of different physical problems, right? So this is a sort of a gentle introduction to what you'll be doing more of next term and certainly next year if you carry on doing physics, right? So this is very close to the way that we typically use calculus in mechanics problems. So the problem we've got is we've got a rod, and we want to calculate, it's a thin rod, so we don't have to worry about its thickness, and we want to calculate what is its moment of inertia if it's rotating about an axis through its midpoint, right? So we want to be able to calculate the moment of inertia there, and so we're going to call the length of the rod L, yeah, and we're going to have it a mass m, and we're also assuming that the weight is uniformly distributed, right? So it's a uniform, the mass is uniform along the length of the rod, right? It's not all clumped at one end or the other end or in the middle, right? So what we have to do is we know how to calculate the moment of inertia for point masses. So what we have to do is we have to break this thing down into a series of point masses. And of course, that means we have to use calculus, right? We cannot avoid using calculus at this point. So what we're going to do is we're going to take a little element of the rod here, and we're going to say, let's take a little element of the rod, delta x. All right, so it's a tiny length of rod, delta x, and we're going to say that that distance, the element is a distance x away from the axis that we're rotating around. Now, if we've got a uniform distribution of mass, then what we can say is we're going to write down well, I'll call it density, but it's not mass per unit volume in this case, it's mass per unit length, right? We'll call that density rho, and that's the mass per length of the rod. Okay, and that's uniform, it's constant along the entire rod. So now what we want to do is what is the moment of inertia of the element that we've worked out there? Well, we'll call that delta I, and that is going to be equal to the mass of the element. Well, if we said the element is a little length delta x, then the mass is simply rho times delta x. So that's the mass. Oops. Right, that's the mass of the element. And then we multiply that, because it's moment of inertia, by x squared. And this is the radius squared, distance from the axis of rotation squared. All right? So hopefully everybody's happy with that so far. But now, of course, what we want to do is, obviously the moment of inertia of this element varies over the length of the element, because here we're a distance x away, and here we're a distance x plus delta x away, and so that's going to have a different moment of inertia. So what we want to do is we want to shrink the element down until it becomes a point. We want to take the limit as delta x goes to 0, and so we take the limit as delta x goes to 0, which implies integration. Right? So what we have now is we have the integral of all the little moments of inertia, right? So that's the integral of this side of the equation, is equal to the integral now of this, which is rho x squared dx, right? And now we're going to put in some limits of integration, because here x varies. So if here's where we've said is 0, right, because we've measured everything, we've defined x as coming from here to there. So this point is 0. So x goes from minus L over 2 to plus L over 2. Right, that's our limits of integration, and we get that from the geometry because we go from minus a half L to plus a half L in x. Okay, well, the integral of 1 with respect to something is just this, is just I. So here we get the total moment of inertia I, and then we just have to integrate this. Well, rho times x squared, where you just increase the power by 1, so we get rho x cubed, and divide it by the new power, that's 3. And then we go from minus L over 2 to L over 2. So this is equal to rho times L cubed over, and then we've got 3 times 8, because 2 to the power 3 is 8, right? So that's just a half. This quantity here is just L over 2 cubed. And then minus rho over 3 times, and now we have minus L over 2 cubed. Well, minus L over 2 cubed is minus L cubed over 8. So this becomes a plus. Right? So what we end up with is this is rho L cubed over 12, because this is rho L cubed over 24 plus rho L cubed over 24, so we get 2 over 24, that's 1 over 12. So that's our moment of inertia. However, our job is not yet done, because we weren't given this quantity, need to replace this, right? Because we're not told in terms of mass per unit length, we were told that the total mass of the rod was m. So if we look at the total mass of the rod, then we know that the density times the total length of the rod, L, right? So that's the mass per unit length times the total length is equal to m. And so what this means is that rho is equal to m over L, right? It's just the mass per unit length. So now what we do is we substitute that in there, and so we get the moment of inertia now is equal to, well, it's mL cubed over 12L. Well, one of the L's cancel, and so we get, as our final answer, that the moment of inertia is mL squared over 12. And that is the moment of inertia of a rod about an axis through the middle of the rod. Now, any questions on that? Because I know that's about as difficult as the calculus in this course gets, right? This is the trickiest bit of calculus you will have to do. Except not just for rods, right? we will be doing other things. Okay, so the trick with calculating the moments of inertia is you break it down to a little element, and then you integrate that element over the entire thing that you're taking the moment of inertia of. So the element that you break it down to has to be something that you know the moment of inertia of, and then you can add all these moments of inertia together for all these little elements by integration, right? So for simple objects like this, I will expect you to be able to do the moments of inertia. So for moment of inertia of a rod, I will expect you to be able to reproduce the argument that we just went through here. Even if the axis is about one end, for example, you should be able to reproduce this here. You might be asked it on an exam, show that the moment of inertia of a rod about some axis is this, right? So you'd need to, from first principles, be able to do this. Another one you'll need to be able to do is that for a disk, right? If we get a chance, I'll run through it later. If not, I'll put it in the worked examples. But there's a similar thing here where you take a disk and you divide it into very, very thin rings. And of course, all the mass on a ring is a fixed distance away from the axis of rotation through the center of the disk. And so, again, you can calculate that, right? So those are the two simple ones. For things like spheres, the method is exactly the same, but to calculate those, you have to be able to integrate. Trig functions. So generally speaking, those ones I won't require you to do because I don't require you to be able to do integrate and differentiate trig functions in this course, right? But so certainly disks, squares as well, flat squares, you can do that. So disks, flat squares, things like that, you should be able to do this from first principles. Okay, but that's about the trickiest bit of calculus there is. Okay, so were there any questions? No, sorry. No, okay, good. Okay, so question for you now with your clickers. So consider these three objects, A, B, and C, all rotating about an axis perpendicular to the flat surface and through the center of them. Which of these three have the largest moment of inertia, A, B, C, or do A and C have the same largest moment of inertia, or all of them have the same moment of inertia? Whoa, okay. No decision. Okay, so turn to your neighbor and try and convince them that you got the right answer. Yeah, just in case anybody was doubtful, they all have the same mass, right? As it says in the question, all of these have exactly the same mass. Okay, let's open the voting again and see if anybody's changed their mind. Oh, we have a winner. And the answer is indeed C, right? C has the largest moment of inertia. Okay, so why is that the case? Well, what we're going to do is look at, so when we're doing this, right, what we're doing is we're taking the object, so here's our disk cross-section, and what we're doing is we're doing what we did up here with maths, but we're doing it conceptually and not worrying about the numbers so much, right? We're just doing a qualitative thing. So what we're doing is you break this down into little elements, right? So this is my little element here, delta m, and it gives me a contribution to the moment of inertia of delta m times r squared, right? Where this is the distance from the axis of rotation. So if I do this, clearly, when I add all of these delta m's together, I'm going to get the same answer each time because each of these objects has the same total mass. But if I look at these three things here, so this is the disk, my r is going to be distributed from 0 all the way out to the maximum radius of the disk. In the case of the ring, the sort of the thick ring, right, I'm distributing my radius from some small value out to some large value, not 0. So clearly, the moment of inertia of this is going to be bigger than the moment of inertia of the solid disk because all the mass that's here on this disk has been moved further away from the axis. And so therefore, by this calculation here, my radius, all the mass that was here in the middle has been moved further away, and so now is going to have a larger moment of inertia. And then in the final case, where I just have a thin ring, all of the mass now is a distance r away, and I have nothing at anything less than r, and so clearly this is going to have an even bigger moment of inertia than the thick ring, because I'm now not going from some small value out to some large value. I've only got the large value, right? The entire mass is located a large distance away, right? And so although the total mass is the same, this r value for each element of the mass, there's some ones with 0 here, there's some ones with small values here, and there's nothing with any small value here, and so this one has the largest moment of inertia, right? So that's the key thing when thinking about moment of inertia is it's not just the total mass, it's where the mass is sitting relative to the axis of rotation, right? You have to worry about both things, total mass and where the mass is located. And that's what makes it different from just simple linear mass, well, normal inertia. Okay, so what about this question? So now we've got two rods, well, the three sets of rods here. So I've got one rod here that's straight, consists of two rods of length L, each pivoted about one end in a straight line. Here I've got them at some angle that's between 0 and 90 degrees. And then here I've got them pivoting, but they're both at 90 degrees, right? So which one of these systems, A, B, or C, has the largest moment of inertia? Or do A and C have the same moment of inertia, or do all three have the same moment of inertia? So vote away. Wow. You guys are good. I've never had a class that got this one before. Okay, you're right. E is the right answer. Well done. Oh, taking away all my fun. Okay, so E is the right answer. They all have exactly the same moment of inertia. So why is that? Well, if we're looking at this system here, what we can do is we can split this down into two rods, right? So we have a rod that's pivoted about this axis of rotation, and we have another rod that's pivoted. And of course, these two things are added together because these are the same axis of rotation that we put them going about, right? So we'll add them together by putting them going through the same axis of rotation. So the moment of inertia of this rod, it turns out, if you do the calculations like this, is end up with ml squared over 3, and it's exactly the same for this rod. It doesn't make any difference the fact that it's at an angle relative to this one. It's got the same moment of inertia rotating about an end of its axis. So we add those two together, and we're going to get the same answer as if we had the two rods pivoting about. Well, I'll draw them with the same axis so it's clear. So if we have this rod here pivoting about this axis and this rod here pivoting about this axis, they'll have the same moment of inertia, right? There is no moment of inertia is a scalar quantity, so it doesn't matter, as long as the axis of rotation is the same, it doesn't matter what the relative directions of these two rods are with respect to each other, right? All that matters is you've got a rod that's rotating about its end, and it has a moment of inertia about its end. And it doesn't matter whether it's angled like this or angled like that. In fact, the best way to think about it is, since this thing is going to be rotating about its pivot point, it'll go through this position and go through that position, and clearly as it's moving round, its moment of inertia does not change. It's got a fixed moment of inertia, and so it doesn't matter what angle it's at, it's going to have the same moment of inertia, right? So the answer is that it doesn't matter what the angle between these rods are. It's you're always going to have the same moment of inertia. Okay. So what we'll do is I'll go through and give you just a few examples of some of the simple ones. I'll probably do a worked example maybe with a calculation of, say, for example, the disk and maybe a square to show you how it's done for some of the other cases. For a ring, for a thin ring with a radius r, it's very easy because all the mass is a distance r from the axis, so it's just mass times r squared, right? You don't even need to do any calculus for this. You can just look at it and say what the answer is, right? Because all the mass is a distance r from the axis. So if you were asked to prove this, you would, of course, have to write down that argument and make it clear that you understood why it was mr squared. But you can do this just by looking at it and knowing all the distance r away. For here, what you have to do is you break it down into elements which are ring-shaped, and then you integrate over all the rings to get the total moment of inertia of the disk. And when you do this, you find you get a half mr squared. And here it's a little trickier than the example we did because your mass is not mass per unit length, it's mass per unit area of the disk. And the thickness of the disk, of course, does not matter. Right? It doesn't matter how thick it is this way, it's only the radius that matters. And then we have the rod. This is the one we calculated. We got a 12th ml squared. If you do it about one end, you get a 3rd ml squared. And we'll come back to this when we do something called the parallel axis theorem. Right? So you can see here that clearly where the axis is matters. Right? And in this case, obviously the moment of inertia is going to be larger because the material out here is a lot further away from the axis of rotation than any of the material here. Right? So you can just by eye, you can see that you'd expect to get a larger value for the moment of inertia here than there. Right? For a sphere, this is a solid sphere, you end up with 2/5 mr squared. For a slab, this one I would not ask you to calculate because it needs calculus. You need to integrate trig functions. It's not that hard. You break it down into rings, into flat disks, and you integrate them, but the radius changes as a function of a trig. So you can't calculate this without integrating trig. And then here you're just integrating rods together, and you can see that the length along the axis doesn't matter. You get the same answer. Right? Because all you're doing is you're just adding together lots of rods, each one which has a 12th ml squared. Okay, so we've got a series of formulae, and if you need them on the exam, they'll be actually told to you, so you don't have to, you can write those down on your formula sheet if you want, but in a question in the exam, if you need to know the moment of inertia for some particular solid, I will actually tell you what it is, so you don't have to write those down. But as you could see there, clearly the moment of inertia depends on where the axis is located. And so the question is, if we've gone through all this hassle of doing calculus to calculate about one axis, is there a shortcut that we can take to calculate the moment of inertia about any axis? And it turns out that there is. So if we take our moment of inertia, we can write it, we have said it was the sum of all the masses times their positions from the axis squared. Well, we can write this down in vector form, and we can say that it's the sum of all the masses times their position vector dotted with itself, right? Because when we do that, we know the dot product of a vector with itself gives you the magnitude squared, and it's a scalar quantity. So supposing this is a moment of inertia about some axis through the center of mass, and that's the crucial point. It must be through the center of mass. Can we calculate the moment of inertia about a parallel axis, a distance r from the center of mass? So what we do is we break this down. So here's our center of mass. This is the axis that goes through the center of mass, and these are our position vectors of all the little points relative to the center of mass, right? But you can write this down now. So we've got our new axis that's parallel to the first one, and it's a distance r away, and this is, of course, a position vector. So now, this blue line here, that what we want to calculate, is big R plus little ri, right? So our new moment of inertia is we'll call it I prime, is going to be the sum over I of all the little masses I times big R position vector plus Ri dotted with big R position vector plus Ri, right? Well, we can expand this out, and so if we expand this out, we get the sum over I times Mi and then big R dotted with big R, right? Plus the sum over I of Mi times Ri dotted with Ri, right? And this, of course, is just the original moment of inertia that we had before. And finally, though, we end up with this term here from the cross product, not from the cross product, from the cross terms here, and there are two of them, so there's a 2 out the front, because the ordering doesn't matter, of mi times ri dotted with big R, right? But if you look at this term here, we can simplify it because r here is a constant, so we can bring it out. So this term here is equal to 2 times r dotted with the sum over mi ri, right? But you remember we said that these little ri position vectors were relative to the center of mass. So if we're doing this relative to the center of mass, this here is the definition of the position vector of the center of mass. So relative to the center of mass, the position vector of the center of mass is 0. It's at the origin, right? Because ri, so this here is equal to 0 because ri relative to center of mass, right? So this adds to give 0. So what we end up with is that our new moment of inertia is equal to, well, this r dotted with r is just the total mass. We sum this over mi. That gives us the total mass times the distance away from the center of mass that the new axis is. So that's just m times r squared plus the original moment of inertia. And so now we have a formula that we can use to move the moment of inertia from one axis to another parallel axis. But the two caveats here that you have to be very careful with when using this problem, and this is something that will be tested on the assignment, is that this moment of inertia has to be through the center of mass. So this is through the center of mass, and if it's not through the center of mass, you have got to make adaptations to the formula, right? So that has to be through the center of mass, and this has to be parallel. You cannot use it for a non-parallel axis, right? You've got to have a parallel axis, and then here this is just the distance from the center of mass of the new parallel axis. And this is called the parallel axis theorem and lets you take a shortcut for calculating moments of inertia. Okay, so I'll stop there. I'll see you all on Wednesday.